Well, howdy ho there, neighbors. Thanks for coming. Appreciate it. Yes, I do. Why am I talking like that? Maybe because I haven't had my Dunkin' Donuts coffee yet. Once I have my Dunkin' Donuts coffee, I talk like a normal human being, sometimes with a British accent, so I sound very weird. Ooh, man, it's good. I love it when it's hot. When it's cold, it's terrible. Guys, it's 8.3. We're almost done with this course. Not really. We got chapter 8, chapter 9, chapter 10, review, and then a test. Test is going to be exciting. My name is Mr. Krause. You can call me Mr. Key, and all these videos will be able to be found at www.nkinfinity.com. N stands for Miss Newman. You can see her picture on our promo. And my name is Mr. Krause, but for the next little while, you can call me Mr. Key, as in Mr. I don't know what the heck I'm talking about. Answer key. No, I'm just kidding. If you haven't hit the subscribe button, you haven't hit the like button, well, how could you like it if you haven't watched it? Watch it, then like it. Or if you know you're going to like it, just hit like and then watch it. Or subscribe. Whatever. Let's get started. Univariate data analysis. Is there anything more exciting? Coffee. At least that's what helps. Univariate. Ooh. Univariate. One variable. We're only going to deal with one variable. Heights, lengths, widths. No regression here, at least now. We're just going to talk about collecting one set of data about something. So univariate, one variable. Ooh, that's simple. How do we analyze a distribution? A distribution is a collection of data. So we're going to collect some data and we're going to figure it out. But you need to understand what's going on. And I'm going to continue to probably harp on this. You can make statistics stay. You can make statistics say... Wow, I need more coffee. You can make it say whatever you want it to say. So you get lied to, and the public always is getting lied to with data because there's really smart people that learn mathematics and they're going to trick you. And they're going to trick you unless you're a discerning, smart person. And I'm going to tell you right now, almost every statistic I read, I have high levels of I don't trust it all the time, all right? Because I don't think people understand how to collect data accurately. I don't think people understand how data is collected. I think people will skew the data to figure out what it is that you want to hear or what they want you to think, right? So as you become better at statistics, you become a little bit more, I can't think of the word, hypervigilant? I don't know. Something like that. All right, shape. Shape. We're not talking about squares and circles and triangles. Go back to 5th grade for that. We're talking about the shape of distributions. Now, distributions can be described as having a symmetric shape. And we'll talk about what that means as we go through these. But symmetry, you all know what symmetry means, right? Cut a line down the middle of your face, the left side should look relatively similar to the right side. A symmetric shape, whatever's on the right side of your distribution should look approximately similar to whatever's on the left side of your distribution. That's it, symmetry. But sometimes they get skewed, right? Skewed. Now, if you skew something, you skew it. When you skew something in English vocabulary, it means you're kind of trying to twist it to what you think, trying to change it in one small direction. So when we skew data, what's going to happen is it's not going to have this nice little symmetric shape. What it's going to have is it's going to have a little part that's way off to the edge here, or going off to the edge, and it's going to drift in one place. And we're going to talk about that as well. So skewness. And when we talk about skewness, and I'm going to talk about this a lot, you're going to really follow the tail. What does that mean? Does that even spell follow? Follow the tail. The skewness follows the tail. And as I go through these, this is going to be something I want you to remember. Follow the tail, right? It's like a dog that found its tail and it keeps trying to chase it, seeing it can catch up to it. That's what we're going to do with skewness. We're going to follow the tail. Can we follow it? All right, some things you need to understand about shape is when we start talking about the center, we're going to start talking about the center. in a minute, and we're gonna address a few things. But these are vocabulary words that you've already been introduced to in the past, and that's median. Median is resistant. That's the word I was looking for. Resistant. Is it A-N-T? A-N-T. Resistant to skewness. Now, right now, that doesn't mean a lot to you. Just take down the notes for now. I want you to understand that. Median is resistant to skewness. So, yeah, we'll talk about it as we go through. We'll talk about it as we go through. Mean, however, the mean, and I just to remind you, mean is the average. That is highly susceptible. Highly susceptible to skewness. Probably should have written that word first because I'm not sure. Susceptible. Wow, that's awful. I can't spell that word. Susceptible. Susceptible. That's it. Highly susceptible to skewness. And this is going to become a very important topic as we go through this. You're going to have to decide, is the median a better indicator of where the middle is? Or is the mean a better indicator of where the middle is? And you have to be able to explain why one would be better or that they're both the same. What we're going to find out eventually is that generally the median is a better indicator of the center of the data only because it's resistant to skewness. Oh, look, center. Now, as we talk about distributions, as we start to analyze distributions, and you're going to find out this is true a lot in your AP statistics course in the future, and that is that you need to have a conversation about what is the shape of my distribution? What is the center of my distribution? How spread out is my distribution? And are there any of these things called outliers? And we'll have a conversation about these, but as we talk about our center, as we talk about our distributions, these are the things that we need to have a conversation about. And you, as a statistics student, need to have a really good grasp at what these four things mean and be able to talk about them. Because as soon as you understand those, you start to understand statistics a little bit better. All right? So let's talk about center. Center. Well, you could say it's the one number this is a good one, to summarize what is typical. Now, a lot of people say, oh, the center's the average. No, not at all. Not at all. We want to know what is typical. What is normal? What do you expect to happen? Based on this data, what's the typical middle or the center of the data? It's not always the mean. In fact, a lot of times it's not the mean. Mean, average, just to remind you, average, is a poor descriptor, is often a poor descriptor of center because it is sensitive or sensitive to skewness. And again, we will discuss that, and you will, I promise you, understand that. However, it is great for calculations. So although it's not a great indicator of where the center is, it is really good for calculations. Let's talk about median. Median, remember, this is the middle number. Generally, it's the middle number. If you line them all up in order, it's the middle number. And this is often a great descriptor. I spelled descriptor wrong. Descriptor of center because it's resistant. resistant to, you think the one thing that's hard, I can do math on these things, but resistant to skewness. But it's bad for calculations. Bad for calculations. Running out of room. Mode, which we know is the most frequent number or most frequent data, it's really only good for, oftentimes it's good for what we call bimodal, or when you have two peaks. Otherwise, not so good. Otherwise, it's really just not a great mode. Mode's just like, okay, there were a lot of these, but those weren't typical. We want to know what's typical. But however, if it's bimodal, for example, one real good thing about mode would be like the average heights of people. Well, it's going to be bimodal. You're going to have the average height of men, and a couple inches shorter, you'll have the average height of women. That would be bimodal, and that's actually kind of a good idea. What would be those? You can't take the average and say the average of people is 5.8. You'd be like, oh, okay, girls are averaging 5.8, boys are averaging 5.8. That's a little short for boys. That's a little tall for girls. No, so maybe it would be a little bit better when we talk about bimodal. Say the mode, it's bimodal. The mode for the boys, or the mode for this group would be, the boys would be over here, 5'10", and the mode for the girls would be 5'8", you'd be like, oh, or 5'6", you'd be like, oh, okay, I get it, they're bimodal. There's a strong indicator down here at 5'6", and there's a strong indicator up here at 5'10", we got bimodal. Otherwise, modes are just kind of useless. Oops, wrong one. I need that for later. All right, let's talk about spread. I don't know where my mouse was. There it is. All right, let's talk about spread. When we talk about spread, we're talking about variability. We're talking about how compact. Is it compact? Is it compact? And then if it's compact, that usually means it's predictable. Predictable. If it's spread out, then that generally means it's not as consistent or it's not as predictable. Now, the measures of spread are range, which is not really range. Remember, the definition of range is the highest minus the lowest. Totally forgot like 6 letters in the middle there. Lowest. This is no good. Totally useless. I mean, does it give you an indicator of how spread out all of your data is? Sure. But, if I wanted to find the average height of people and I walked into a, if I want to see how spread out the heights of people are, and I went to, a basketball arena, and I said, okay, I want to know the average height of people. Well, the shortest person in there is probably going to be about 4'10". There's always somebody that's short. And then the tallest person is probably going to be like 7'2", right? And we say, oh, look, the average height of people range from 4'10" to 7'2". No, that's not really where most people lie. Most people are going to be between 5'8", like 5'3" and 5'11". You're going to have like 90% or whatever the number is between those two numbers. And then you're going to have some people that are a little bit taller. And then you're going to have the crazy fringe people that are just so far out there that they would be almost considered outliers. So range is sort of not very useful. A better indicator than range would be what's called the IQR. This is called the interquartile range. Interquartile range, or the IQR, and this is Q3 minus Q1, where we'll talk about it, and you probably already remember this from your earlier statistics, and that is your quartile 3 minus your quartile 1. Well, that's going to represent 50% of the data. That's the big 50% of the data, and that's really a good indicator of, okay, what's typical, what's normal, what's the normal spread? Most of the time, however, we'll use this thing called standard deviation. And we're going to talk a lot about standard deviation over the next few days. Why am I having a hard time? I'm having a hard time spelling this stuff today. I don't know why. Deviation. I got it. Standard deviation. And we'll use that. This is the indicator. This is the sigma. That's the variable, sigma. That wasn't a very good sigma. But I'll draw them so much you'll be seeing what they look like. If the standard deviation is small, you have very condensed or predictable data. If it's wide or large, if you have a large standard deviation, this is spread out. So as we start talking about our spread of data, you're going to have to understand a standard deviation of that's a small number means you got all the data is going to be really close. Whereas a standard deviation that's a big number means we're going to have really spread out data. And you also have to be really smart about a couple of things. I might say a standard deviation of 10 is small. And a standard deviation 10 is large. What? How can a standard deviation of 10 be small and a standard deviation of 10 be large? Well, you got to understand where the population is. If I said a standard deviation of the weights of elephants is, there's a standard deviation of 10 pounds, I'd be like, oh, okay, that's fine. But if I said there's an average standard deviation of, children under 5 is 10 pounds and the standard deviation is 10, that's huge, right? Because kids weigh, under 10, they only weigh like 80 pounds, 70 pounds. If the standard deviation is 10 pounds, maybe that's a pretty big number. But for elephants, that would be a teeny tiny number. So, you got to understand what the population is and what the number represents. Could it be 10 ounces? Could it be 10, microns? I don't know. So just because the number is 10 doesn't mean it's big and the number 0.1 is small. Who knows? 0.1 sometimes is a very, very large standard deviation. And you'll get that as you go through and get better statistics. You'll understand how that works. Outliers. Outliers, otherwise known as mavericks. Outliers, by definition, and what we're going to use as our definition is, let me just say, outliers occur, that's the word I was looking for, occur outside of the range. Let's try to put those two words together. The range. Standard deviation. Oh, wait, excuse me. 1.5. And I should probably put plus or minus 1.5 standard deviations away from Q3 and Q1. So what I mean by that is if you have 70 or 50% of your data between Q1 and Q3, and then let's say your standard deviation, takes you out a little bit. Let's say your standard deviation is a certain length. There, that's my standard deviation. Well, if I go 1.5 standard deviations past that, so a little bit more, halfway more, and I got some number out here, this might be an outlier. They're found way on the outside on the fringes. They're just things that are so atypical, not likely, that we have to call them outliers. If we're in a high school classroom of, I remember my son watching him walk across graduation in 6th grade, or moving up ceremony or whatever they called it. And, you see this, this file of kids, all boys, all the same height. They're all 4 foot, 10 or something like that. And then all of a sudden, this one kid, great kid, loved the kid. He was also a great trumpet player. All of a sudden, this one kid, he was 6 foot tall. In 5th grade or 6th grade or whatever it was, he was 6 foot tall. He was a foot above everybody else. Well, clearly, if I was going to do the distribution of all the heights, all the kids' heights are somewhere around 410, right? And, maybe their standard deviation was 2 inches, and you catch a few of them at 2 inches, and then you catch a few more at 2 more inches, and we'll talk about standard deviation. And then we'll talk about the fact that within like 6 inches, you should have almost every single kid. If the average is 410, and you go out like 6 inches up and down, you're going to get like every single solitary kid. Well, there was this one kid. All of a sudden, he was way out at 6 foot tall. You're like, okay, and you can see it. He clearly stood out as an outlier. And outliers happen a lot on tests, too. You'll get most of the kids who do really, 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 really good, and then you get maybe one kid just did freaky good. Now, often it's harder to get an outlier that's way above, but oftentimes you will get an outlier that's way below. This kid that just doesn't study, doesn't do his homework, doesn't care, and they'll get such a low grade that they're so far away from the rest of the class that we sort of don't want to use that one, right? So if my administrator was walking in and they said, hey, how's your class doing? I said, well, they're doing pretty good. Most of the kids are between 75 and 90, or maybe most of the kids are between 85 and 95. You got a great group of kids working hard. You got a few near 100. You got a few in the 70s, maybe a couple in the 60s. And then you got this one kid, or two kids that are down there at the 30 and 40 level that just aren't doing what they're supposed to be doing. You know what I'm talking about. It's in almost every classroom. You got that one kid. Luckily, I've had great classes these last couple of years. I haven't really even had it. But that one kid. Now, when you want to describe how your class is doing as a whole, you'd say, okay, those kids, they're just not doing what they're supposed to be doing. They're outliers. They are so far away from what is normal in this classroom that I just can't count them. And it's got to be mathematically provable. You got to say, okay, here's my standard deviation, and we're going to talk about this. They're 1.5 times outside of quartile 1 and quartile 3. Not from the median or not from the mean. They're outside quartile 1 and quartile 3. Outside the 25% and the 50%, they're so far away that they shouldn't count in the data. All right. If describing, then we use if describing, I'm just trying to figure out if there's something else I want to tell you. Then we use IQ and median, but if calculations are wish to the mean and standard deviation. Okay. All right. So one of the big things before I leave this little notes page is skewness and means don't mix. It's kind of like drinking and driving don't mix. Don't. That's my shorthand for don't. Skewness and means don't mix. If the data is skewed, don't use the mean. And we're going to look at that in the next page and see what that looks like visually. Sorry, kids. Needed to get a little caffeine boost. All right. Let's look at these distributions. Let's look at these frequency histograms, or these histograms that you see here. And remember what I said. Skewness follows the tails. Oh, I have it right here. Skewness follows the tail. Remember, it's like a dog that's following his tail. So, let me get a different color. So, as I look at this data, let's start with the middle. You've seen this graph before probably, right? This is the normal distribution curve. Normal distribution is most people are in the middle. Right? If you're looking at a test, most kids are doing well on the test. You got the scores between 75 and 85. Then you got your group that are between 85 and 95. And then you got those crazy smart kids that are between 95 and 100. But there's not a lot up here, right? And then you got those kids that, they're struggling, they're working hard, but they're between like 65 and 75. And then you got these kids over here that are between 55 and 65. But most of the kids, the vast majority of the kids are here. Now, that doesn't mean, symmetric doesn't have to mean that doesn't have to mean normal. Normal and symmetric, they're not the same. Things that are normal are symmetric. But just because it's symmetric doesn't mean it's normal. You'll see that in a picture that's coming up later. Just want to make sure you understand it. But normal distributions, it's normal to have most people in the middle, and it's not normal to have people way at the top, and it's not normal to have most people at the bottom, but there will be some. Now let's talk about skewed left. If the data is skewed left, again, we follow the tail. So if I was to draw a picture over this stuff, it would look like this. And here's the tail. And it tails off this way. This is the tail over here. So when I say skewness follows the tail, what I'm going to say is you need to describe the center, shape, spread, and outliers. And you need to decide, the first one you're going to describe is shape. And here's our shape: skewed left, symmetric, or skewed right. In this case, you would say skewed left. It's skewed left because the tail is off to the left side. And what do I mean by that? What I mean by that is something's trying to pull the averages down. It's trying to skew normality down to the bottom. So you're skewing it or pushing it off to the left. Oops, to the left. I forgot I'm talking to you guys. I'm doing my left, not your left. So skewness off, you're trying to push it off to the left. Right? This over here is skewness to the right. Notice my tail on this case is off to the right. Now, one of the things I want you to notice is on this one, the average is right here, 3.5. Now notice what's going on here. Your average here is 5, somewhere around here. But your mean is 5.5, which would be somewhere probably right about here, right? This would be my mean. So this would be my mean or my average. And we use this terminology, I'm not sure if I used it the other day, called X bar. Just to remind you, it's called X bar. So the X bar is 5, or the mean. Notice that the mean, because it got skewed to the left, the mean got pulled down a little bit. Over here, notice that the median and the mean, they're not always exactly the same, but generally, if it's symmetric, they are in fact going to be the same. And over here, the mean is 2, but the median is 1.5. This would be the most middle of data, right? If I took all of these little pieces here and packed them up, I would probably be right about here, right? Well, then the mean should be closer to here, not over here. But because it's skewed right, that means the mean got pulled over to the right. Does that make sense? You know, let me give you an example mathematically. If all the numbers were like 20, 22, 24, 26, 28, and then all of a sudden you had a 50 and a 55, or numbers way off here to the right. Well, you know, the middle of this data, the middle of this data is 26, which looks to be more typical of what's going on. But if I tried to do the average, because these numbers are so big, the average would get pulled up that way. And I think you guys understand enough about numbers that if you add in a bunch of high numbers to a bunch of low numbers, it's going to bring that average up. So remember, mean and skewness don't mix. So because this is skewed here, I do not want to use the mean. I would choose the median because it's skewed. Because this is symmetrical, it really doesn't matter which you pick. It really makes no difference which one you pick, mean or median. And because this is skewed to the right, again, mean and skewness do not mix. So again, just to recap a little bit, a mean is a poor descriptor of center because it is susceptible to skewness, or sensitive to skewness. Probably should use sensitive, and outliers. But it is great for calculation. So we're going to see how we can, and you're going to, over time, and the more you spend time, calculations, over time with statistics, you're going to see how you can avoid skewness and outliers and things like that. The median is great descriptor of the center. So it's a great descriptor of the center. Because it's resistant to skewness. Resistant to skewness and outliers. And I'll show you one more example of that in just a second. But not good for calculations. So if you're going to do some mathematics, you're going to have to, you're going to have to do some hand calculations. We're going to want to use the mean, not the median. So not good for calculations. Calculate. Do I need to really spell that out? Can you spell calculation? Let me see how neat I can do it. Calculation. See, if I go slow, I think I can do it. Let me just give you one more example. 2, 3, 4, 5. Now, you guys are smart enough to know that the median is right here in the middle. Oops, I don't want to use that one. At 3.5. Now, let's say I add 100, the number 100 to it. Now, I'm looking at this data, and I got 2, 3, 4, 5, 100. Now, for these, the average would be 3.5. If I just looked at these, the average would be 3.5. The median would be 3.5. If I add in this 100, now the average goes to, I don't even know, that's 109, 112, 114, 114 divided by 5. What is that, 20-something? The mean in this case would be, or the X bar would be like 20-something. 22 or 21. It's like 22.8 or something like that. Right? But that's not really an indicator of what this data is, right? This 100 is just freaky crazy huge. But the median would just be 4. So although I added this crazy outlier that took the average, right? If you said to somebody, hey, the average of those numbers is 20, I think it's around 22. If you said the average of those numbers is 22, and you 2, 3, 4, 5, and 100, and the average is 22, and you're like, oh, or you were saying to a friend, hey, you know what? It's typical to get about 22. With this data right here, it's typical to get 22. Your friends would look like you're on crack, right? You're not. It's not typical to be 22. What are you, crazy? Typical will be about 4, right? And then so you can see how adding in a crazy outlier or a maverick or a number that's so far away from where it's typical would really screw up the mean. So means are really susceptible to outliers and skewness. All right. So, as I promised before, let's talk about these. This is symmetrical. And it's relatively normally distributed. This is symmetrical. Not normally distributed. But what do we call this? Well, it's just symmetrical data. It's very symmetrical data. And you know what? This is symmetrical data. However, although they're all symmetrical, their spreads are completely different. Let me show you what I'm talking about with this. And I think sometimes it's easier if you see it as a curve. And what I'm going to do, I'm going to take my fisherman's net out. So I got my fisherman's net. Maybe that's too big. How about this? I'm going to take my fisherman's net out. My net's going to be about like this. All right, and I got my net. So if I was to take my net, and come up to this one right here, and I drew it around this one, let me do it in this color. If I drew my net in this color, and I go, okay, here's my net. And I'm going to start here. And remember, so I'm just going to bring my net up. Do you see that I collect all of this from here to here? I'm collecting almost all of this data just with that net. If I just swoop my net up, I collected all of that data. What didn't I collect? I didn't collect this stuff out here, and I didn't collect this little bit out here. So now I'm going to use that same net over here. About the same size, right? But you'll notice this time I'm only collecting this much right here. Look at this big piece I missed, and look at this big piece I missed. I did collect this big piece in the middle, so I did collect all this. So I have collected all this. But I missed this huge piece over here and this huge piece over here. And then let's finally get this same net here, right? Same net size, trying to at least. I'm going to collect in this. But notice that middle chunk's kind of tiny now, right? So look what I'm missing now. I'm missing all of this, and I'm missing all of this in my net. And that's why, my friends, that this is the most spread out. While they're all symmetrical, the ones that have all their data near the middle, like this one over here, the ones that have all their data in the middle, you can capture most of it with a net that big. This one I'm only capturing this, but I'm losing all this stuff on the outside. And this one, I'm capturing all of the same net size, but look at all the stuff on the outside. The ones over here, these off here, where you have the peaks on the edges, when you have the vast majority on the edges, that means you're going to have a really high spread, which means in terms of math, you're going to have a really high standard deviation. So I graphed this data, and just as kind of a little tutorial. Let me see if I got to take a break. I'll be right back. Well, I typed it all in. Oh, coffee's getting cold. So what I did was I typed all this data in. I don't need you. I typed all this data in. And it's going to look like this, but I want to really make sure you understand how to get it. So, of course, you're going to go into your spreadsheet mode. And then you're going to go into Doc. Let's see, what is it? Insert. Data and statistics. And you get a whole bunch of dots here. I can create a dot plot of the concentrations. There's a concentration dot plot. But oftentimes that's not very useful. So I'll come over here to menu and I'll say, okay, what kind of plot type do I want? I'd rather have a histogram, because a histogram is great for checking out spread. That dot plot's not bad for checking out spread, but this is a much better indicator of checking out spread. And the animation's kind of cool. So if I look down here, I can see that it's relatively symmetrical, right? I might have a little bit of skewness off to the left here, but it's not bad. Let me go check out my data. Let me see if I got plug these in right. Let me go back to here, and I want to do I'm going to do one variable statistics. So I'll go menu, statistics, stack calculations, one variable statistics, okay. I think we called it concentration. Click OK. So there it is. Looks like it matches the stuff that's on my chart. So let's talk about this data. So what it was this is swordfish absorb mercury into their bodies, and the concentrations in parts per million. Apparently 1 part per million is not good for human consumption. So if the swordfish have too much mercury in their body, mercury is not good for humans. So if I look at this data, and I thought you were given this, but apparently you're not. So let's put this in here. If I go back to my chart over there, I'll figure out that the X bar, which is the average or the mean, is 1.08. My sample standard deviation is 0.475795. Now this stands for my sample standard deviation. And why is it sample? Because I didn't test every swordfish. I only tested this, 28 swordfish. All right, let's see what else we got here. My min is equal to 0.07. My quartile 1, this is often called my 5-number summary, starting right now at the min, 1.1, oops, excuse me, my quartile 1 is 0.085, or 0.815. My median is 1.11. My quartile 3 is 1.385. And my max, which is 2.10. And this is often called the 5-number summary. 1, 2, 3, 4, 5. I can make a box plot from that. You've probably done that. But I also want to check for outliers while I'm here. So outliers. Outliers. I want to do hold on a second. Yeah, you know, I misspoke earlier. So go back to these notes. I think I just realized I misspoke. Yeah, it's right here. I said 1.5 standard deviations. I think I meant 1.5 IQRs away from the Q1 and Q3. Yeah, I knew I messed that up. I apologize. It's not 1.5 standard deviations. It's 1.5 IQRs times the IQR. So if I take the quartile 1, which is 0.815. Let me find the IQR first. IQR is defined as Q3 minus Q1. So in this case, it's 1.385 minus 0.815. So if I grab my calculator, 1.385 minus 0.815, and I get Control Enter, 0.57. So if I want to come back here, this is 0.57. So if I want to come back here, my outliers would be 0.815 minus 0.57, which is, this is the IQR, remember? I keep screwing this up, remember? So an outlier is defined as quartile 1 minus 1.5 times the IQR. I forgot to multiply by 1.5. So 1.5 times 0.57. So if I go to my calculator, I'm going to go 0.815 minus 1.5 times 0.57. Of course, it's going to be negative 0.04. So this is negative 0.04. And then I'm going to take 1.385 and I'm going to add 1.5 times 0.57 just to get an idea if there's even a remote possibility that I have outliers. 1.385 plus 1.5 times 0.57. Enter. Control Enter to get the exact 2.24. So if I have anything lower than negative, which you can't have negative mercury levels because you either have 0 or you have some, and 2.24. So let's see. Nope, doesn't look like I have any outliers. There's nothing below 0.07 and there's nothing above 2.10. So there are no outliers in this. So as a mathematician, you need to describe this data. We're going to describe it with center, shape, spread, and outliers. So let's go through this. This is how you would do this. The data on, what is this again? Mercury levels is fairly symmetrical. Is fairly symmetrical That's good enough. We talked about it. It's got some symmetry. The center of the data as described by the median is 1.11. The data, the spread, and so you notice you're going through and you're describing each one. The spread of the data as the spread of the distribution, the spread of the distribution as described. Man, I'm having a terrible time spelling today. It's described. No comments about my poor spelling or my poor penmanship. You try doing this. This guy's tough sometimes. It's described by the IQR is, what was our IQR again? 0.57. Is 0.57. This distribution does not appear, appear to have any outliers, since we have no data outside the range 0.04, negative 0.04 to 2.24. So you're not going to be given these nice little colored bullets off to the outside. You're going to have to create like a small little paragraph at the end describing this shape. You'll get some data, you'll come up with it, you'll create a histogram. I'm not going to create the histogram for you. And you'll have to say, okay, the data on mercury level is fairly symmetrical with a center as described by the median of 1.11. The spread of the distribution as described by the IQR is 0.57, and because we have no values outside the range of negative 0.04 and 2.24, this distribution does not appear to have any outliers. Boom. You have described center, shape, spread, and outliers, and you have done a very good job of describing what this distribution looks like. And you're on your way to now understanding more about what you can do mathematically with it, or what you can't do mathematically with it, or what predictions you can make with it, or what predictions you can't make with it. All right, so let's take a look at the next page and we'll see how we can do some more of the center, shape, spread, and outliers. I think if I were you at this time, I would, pause the video and see if you can come up with center, shape, spread, and outliers. Now, just do a quick sketch. What I'm looking for, let me do one of them. This one is symmetrical. Symmetrical. Or symmetric. What would you use? You can use either the mean or median. Generally, you use the mean or the mean. Use the mean or the median. Generally, you use the median, but in this case, you could use either. Spread, we would use the IQR, and my guess is there would be no outliers. And is it fairly spread out? No, it's pretty compact. So in this case, it's relatively compact. So the IQR would be relatively compact. You guys try that for the next three. So pause it. Yeah, no, go ahead, pause it. No, go ahead. Oh, you're back. Oh, okay. So on this one, shape, this would be, remember, we follow the tail. So it's not good enough to just say skew. You have to say skewed right. You follow the tail. So if you want to, you go, oh, there's the little tail right there. So follow the tail, skewed right. The center, in this case, you would have to use the median. Anytime you have skewness, you have to use the median. Spread, again, we would use the IQR, but this is a little bit more spread out. It's not too compact. It's kind of spread out. Obviously, we're going to use the IQR every time, but this case, it's kind of spread out. And are there any outliers? I would say no. There really aren't any outliers. More than likely, if you were going to have an outlier, you'd have maybe none here, and then maybe this might be a little outlier here. But generally, probably not. In this particular case, there doesn't appear to be any really freaky, crazy people over here getting 120% on that test or whatever it is. This one, again, you got to tell me which way the tail's going. This is skewed right. Excuse me, skewed left. Because the tail's going off to the left. Center, again, we have to use the median. We would use this IQR, but it's the IQR, and it's kind of spread out. It's a little bit more spread out. It's not too bad. And probably not. No, there's no freaky, little bars way over here where they're so far away from everybody. That's where you're looking for outliers. Center, this is symmetric. Remember, if you draw a line down the middle, it kind of looks the same on the left and the right. Kind of. It's kind of got the same general shape. In this case, the mean or the median would be okay. Because when it's symmetric, either one is fine. Generally, again, we use the median. It's a better indicator. But you could. Because this one is bimodal, you got a piece down here and you got a clear piece up here, you might even want to use the mode. Depending on what you're looking for. Again, if you want to describe this, what's typical here, you'd probably want to use the mode because you got peak here and you got a peak here. So the mode might be a good or a better indicator of what's typical. If you're going to do some calculations, then you probably want to use the mean. Probably the median's not very useful here, actually, if I think about it. IQR, yeah, but this is really spread out. This is really spread out. Because the bulk of everything is on the outside, way out here, it's really spread out. But there are no outliers, none. Outliers are so far away from what's typical. These are typical and these are typical, but there's really nobody so far away. So very quickly, which distributions have a mean that's less than the mean, that's less than the median? So one of the things we're going to want to look at is, the skewness pulls mean. So if the mean is on the left or less than, then it's got to be skewed left. So in this case, we're going to skew left. So skewed, I forgot the ED. Skewed left. So if the mean is to the left of the median, that means it's being pulled to the left. Which distributions have the mean close to the mean? These are symmetric. And which distribution has the largest standard deviation? These are symmetric distributions, with the bulk of data on the fringes, let's say. You have a bulk of the data here, and you got a little bit in the middle, and then you got a bulk of the data here. If this is my distribution, this would be where it would be a symmetric distribution, but the vast majority of the data is out on the fringes, out on the outside. All right. Here are the heights of the boys. Determine the shape of the graph and describe its center, shape, and spread. I didn't give you this. Oh, so if I went through and put this in my calculator, you'd find that the x bar was equal. Well, let me stop and come back. All right, so if I was to put this data in my calculator, here's what I would end up with. 72.2 is my mean. My sample standard deviation is 2.973. My min is 65. My quartile 1 is 72. My median is 73. My quartile 4 is 74, and my max is 76. Now, again, I've got to talk about center, shape, spread, and outliers. Now, one of the classes I was watching the other day came up with the acronym SOX. Center, outliers, center, and shape. Just to remember what they are. Usually we do outliers last, but center, shape, spread, and outliers. So it's not good enough to just think you know. You have to mathematically prove. So I need to first figure out what the IQR is. In this case, the IQR is the difference between these two, which is 74 minus 72, which is just 2. Now I want to determine if there's any outliers. So I'm going to do my outlier work. So I'm going to take 72 minus 2, and I get 70. Or I'm going to take 74, and I'm going to, whoa, let's back up the crazy train. I just did it again. It's 1.5 times 2. Let's see, 1.5 times 2 is actually 3. 72 minus 3 is 69. And then 1 plus 1.5 times 2, which is going to be adding 3, that's 77. So if I have any outliers, they have to be outside of that range. Clearly, this young man is, or I guess these got to be guys, has to be an outlier. So if I was to describe this, and I'm just going to say this out loud, I'm not going to try to write it because I think you'll get it. And I'll maybe pause it, write what you think, and let's see if it matches what I think. You should pause it and write down what you think, and then we'll see if it matches what I'm going to give you. Go ahead and pause it. All right, here we go. I would say, I'm going to read off what I wrote so I make sure I don't miss anything, because oftentimes I would just write it and make sure I have everything. It says the distribution is relatively symmetrical with a center measured by the median or the mean of 73. I would do median. So I would say the center represented by the median to be 73. The spread of the data as represented by the interquartile range would be 2 inches, which is relatively compact based on this data. Outliers will occur outside the range between 69 and 74, or excuse me, 77. Therefore, we have one player on this team that is an outlier, and that's the young gentleman with the height of 65 inches. Something to that effect would describe this data. So if you were to come by, if I was to come by and say, describe what this team would be like. Now, first of all, you're not going to describe it like that to a sports reporter, but a statistician would really want to know that. It's relatively symmetrical. That means the bulk of your player athletes are going to be there in the middle. With a median of, with a standard deviation or an IQR spread of 2. That means most of the kids are within 2 inches of the median. And the last thing is we have one player that is an outlier. So if I was coming there, I'm probably going to see one kid that's either going to be freakishly tall or freakishly small in that group. And then when I'm walking around, I go, oh, there's the one kid who's the outlier, and I can see what's going on. That would be a very good description of this distribution. All right, hopefully you got a lot out of this. Hopefully you understand SOX, center, shape, spread, and outliers. All right, kids, hit the subscribe button, hit the like button, and keep coming back. There's more to come. Goodbye.